Hi to everyone and welcome to this AMETEK Land webinar. Okay, right now I'd like to introduce today's presenter, Mark Bennett. Mark is a qualified mechanical engineer majoring in fluid dynamics and heat transfer. He spent 13 years working in research and development in the UK nuclear industry before joining a technical sales and marketing team specializing in measurement and control. Now, Mark joined AMETEK Land in 1996 to support its sales channels in providing accurate infrared temperature measurement solutions. Now, as glass sector lead, he focuses on providing accurate, high-temperature measurement in challenging and harsh industrial environments for the glass industry. Mark is an active member of the Society of Glass Technology and a member of the Melting Technical Committee. Mark, welcome to today's event, and with that, I'm going to pass things over to you to get us started.
Good afternoon and welcome to this Engineering 360 webinar on infrared temperature measurement in the glass industry. My name is Mark Bennett. I'm actually a qualified mechanical engineer studying and majoring in fluid dynamics and heat transfer. I like to tell people that I actually started working with infrared temperature measurement back in 1976. Went to my first training course at Land Instruments in 1986, joined the company in 1996. So I've had a lot of experience measuring different applications, different measurement techniques in the infrared industry. Just to introduce the company very quickly, Land Instruments was established in 1947 by a physicist, Tom Land, and Tom found that in the industry generally, there were a couple of suppliers of infrared thermometers, but our customers, the steel industry at that time, wanted a more accurate and reliable instrument. And Tom set about providing a company which could provide the most accurate and stable solutions for all industrial sectors. And there were many industry firsts that have come along as a result of the work that we do internally in the organisation. There's a great deal of work spent on the research and development, and as you can see there, the industry firsts keep coming and coming. So before we get to look at some of the applications in the glass industry, what I'd like to do is just cover some of the basic theory and what we are looking to measure with thermal radiation. And of course, for some of you, this is a new subject, something you're not familiar with. But thermal radiation is something that we all are familiar with. It's something that we can feel. It's the radiation we feel coming from a radiator or from a hot fire. And what we need to think about is that all objects, so this is everything above absolute zero, is emitting electromagnetic energy waves that we can make use of if we capture them and relate that signal to an output. When we look at the electromagnetic spectrum, the electromagnetic spectrum is something that we're all reasonably familiar with in our day-to-day lives, with X-rays, the visible light spectrum, and indeed radio waves all cover what is the electromagnetic spectrum. Now, the section that I'm particularly interested with is what is the section down here, which is the infrared section. And what you notice is that the infrared section also covers the visible section. So our eyes are actually very good infrared detectors. If you think about looking at a piece of steel or something heating up, what you often see is that it changes from what is its natural colour to be something which appears to be red to the eyes. And the reason that it appears red is because it starts emitting energy in this region here that our eyes see as red light. As the object gets hotter, it starts emitting orange, and eventually we call it white hot because it's emitting energy over all the wavelengths that our eyes can see. So the traditional light bulbs, the incandescent light bulb, has a filament, a tungsten filament, which is heated until it is glowing white hot, and that's what our eyes see as being the visible light. It's emitting energy over the area that our eyes are sensitive. Now, if we look at the basic theory of infrared temperature measurement, there's a very important set of curves. The curves that I'm showing you here were first drawn by Maxwell Planck, and this is Planck's law. So a lot of the radiation theory that we work and we develop on is based around Planck's law. And what you can see here on the screen is that there's energy being produced over a very wide range of temperatures. So if we look at the wavelength of that energy, what we can see is that at 1 micron here, which is where our eyes are operating, at the lower temperatures there is no radiation visible to the eye. As the object heats and heats, what we can see is there is energy then being produced that our eyes see as being the red and eventually white heat. So this actually shows us quite a great deal of how we use infrared thermometers out there in the field. We can use our eyes for making certain judgments, and we'll look at that later in the webinar. So the first thing to perhaps just look at and just understand is, how do we measure infrared energy? How is that measured by a thermometer, by a device that's giving us something that we can relate to temperature? So in this example here, we have a typical target, and what we tend to think of is that 100% of the energy comes to the surface of the target, and in this instance 96% of the energy is escaping and 4% of the energy is reflected back internally. Now, this is an effect that we know and we can prove because different materials cool at different rates. So if you consider a block of aluminium or aluminum compared to a block of steel, then we know that these items will cool at a slower rate. And what we're looking at here is the effect of that difference in cooling. Now, if we are to relate that 96% of energy that our detector receives back to temperature, we need to calibrate the device somehow. And the way that we would do that is to take the instrument to a calibration laboratory. And a calibration laboratory has a device which is called a black body furnace. And a black body emits total radiation. So this is 100% of radiation over all temperatures at all wavelengths. So that's quite critical, all temperatures and all wavelengths. And what we do is we can then relate the output from our detector to equal some function of temperature. So what we need to recognize at this point is that the emissivity value, which is a ratio value, is the radiation emitted by an object at temperature divided by the radiation emitted by a black body at the same temperature. So this term that some of you are familiar with, emissivity, is actually a factor which relates the real world back to our calibration laboratory. And the output from our detector then becomes equal to some function of temperature times this emissivity factor times the area over which the measurement is made. So if we look at that as an equation, the output equals some function of temperature times emissivity times area, and then we look at our example here where we have 96% of the energy coming to our detector. What we need to remember is our relationship, that the emissivity relationship that we've calculated either from looking at the reference tables for emissivity, or we have a known factor which has come from evaluation, from history, or indeed Land can provide you with an analysis of emissivity of your specific material. But what's important to recognize at this point is that the emissivity is applied to the nonlinear detector output. And what we do is we divide that output by the factor of emissivity, which is the 0.96 in this case. So the example here is we're using an emissivity factor of 0.96. and that means that the output from this amplifier here is being effectively multiplied by this 0.96 factor. So we add artificially 4% of the signal. And then within the thermometer itself, we apply a linearizer, which gives us a 4 to 20 milliamp output from the thermometer itself. So what are we here to look at today? We're looking at what is the glass sector. And glass is quite a phenomenal material. If you look around, glass is actually everywhere. It's in the vessels that we drink from. It's in the windows that we use to look out into the world. It's in the windscreen of our cars. It's even in the spectacles that we wear for seeing. So glass is a very, very important material. Some of you might not realise, but the materials that we use for strengthening are often fibre. So the glass fibres that we produce, high strength glass fibres, are used for example, strengthening the blades of windmills, and indeed in my own vehicle, my own car, the cylinder head, the aluminium cylinder head block has reinforced glass fibre in that block to give the block strength. So glass is almost everywhere, and it is the ultimate recyclable material because we can reheat, we can remelt, and we can reuse glass. So in our current global concerns of the environment, glass is a very important material going forward. And it's something that we need to look at and improve the material science around glass, because we've been making glass pretty much in the same way right since the Roman days. There's a lot of work to be done in improving the production of glass and how we move that forward in terms of efficiency of production. So what exactly is glass? Well, believe it or not, the basic form of glass is liquid sand. So what we're doing is we're taking sand, which forms the vast majority of the what's known as the batch. The batch is what's put into a big melting furnace, and we heat that up to temperatures of around 1700 C, 3090 F, and from that we will form the batch forms or dissolves into what becomes molten or fluid glass. Now there are many different compositions of this batch, the base raw material, that form lots and lots of different glass types. There's some examples shown on the screen now, and these are just from Wikipedia, but they give you quite a good understanding of what are the main glass that we would use. So predominantly the biggest glass that we have in the system is soda lime glass, and then we also have borosilicate glasses, which are the higher chemical resistance glasses that are used. So I've just highlighted those two as being some examples, and if we look at what is the soda lime glass, what you can see there is that predominantly the largest component part is indeed the sand, the silica. But there are a number of other component parts that make up the batch. Some of these are for forming specific types of glass, whether it's a different color, different strength, different properties, and that's where the batch is made from. There is also some additives which help with the melting, so the dissolving of the glass by forming a wetting process around the materials. It allows them to dissolve into the process more readily. So let's start our application part of this webinar, looking at what is the start of the process, which is the melting of the sand. And the melting of the sand occurs in what is known as the glass tank. And the glass tank, as I've said in my previous slide, is heated somewhere in the region of between probably 16 to 1700 degrees centigrade. So this is a process which pushes the boundaries of containment and creates a number of challenges in the real world. And what I have here is some examples of different configurations of furnaces. Something that's called an end-fired furnace, because in this example here we have burners mounted in these locations here, firing into the furnace. And in an end-fired furnace, the burners on each side fire alternately. So every 20 minutes there is something called a reversal. During the reversal time, the flame is extinguished and the reversal of the flames occurs. And that we do that because the waste gas, the gas is taken into the regenerator. This is the regenerator section, and energy is stored, effectively stored in the regenerator, and thus can be brought back into the process without wasting the energy. So in a cross-fired furnace, it's exactly the same configuration. However, now we have the burners pointing across the furnace, and again, every 20 minutes we get a reversal cycle and we switch to the other side of the furnace. In the glass industry, we always talk about the direction of flow of glass. So from the input of the batch, the glass flows through the tank out into the distributor in this example here. Now there is a move in industry to try and reduce what are the emissions from the process, and the modern new design of tank is what's called a recuperative furnace. And in this furnace, the flames run continuously, but they are what is known as oxy-fueled furnaces. And with an oxy-fueled furnace, what we do is we burn the fuel using pure oxygen, and this reduces the NOx values within the exhaust gases, and again is a green solution for our planet. Now, when we look inside the glass tank, what we have to recognise is this is a very complex thermodynamic model, and the glass flow within the glass tank is absolutely critical. So you can see in my diagram here, we show the glass circulating under the surface in two different directions under the surface. And we have something that we create here, which is called the spring zone, where the glass comes to the surface. So the basic melting and dissolving of the glass occurs in this region, and this section here is more refining and removal of gas from the glass composition. Now, to drive what is these thermosiphons under the surface, the primary goal is to create a temperature profile along the crown of the furnace and along the side walls of the furnace. And the key element here is to create what's called the hot spot, which occurs above the spring zone. So as you can well imagine, the temperature control, temperature monitoring, flame management is very important within this environment. Now, traditionally, and if you go to most glass plants everywhere in the world, the Cyclops Portable has become the industry standard for monitoring temperatures and monitoring temperature stability within a glass tank. And you'll find that almost every glass company in the world shoots a single point using the Cyclops 100L, the 2F version, which has got integral eye filters designed for use in very hot environments, and particularly in glass tanks, because if you look into a glass tank without protection, you will damage your eyes. The Cyclops allows us to take an accurate temperature measurement from a reasonable distance at a very precise location. This has through the lens optics very similar to a camera. In fact, the original lens, the lens that's on the front of this device, was designed by the Minolta camera company, to give you an idea of the quality of optics and why this instrument is used as standard. So once a shift, at least once a shift, a single point measurement will be made to check the overall temperature and compare the overall temperature of the glass tank on a trending basis. Now this is to compare with the blind thermocouples which are mounted in the crown and along the breast walls, along the walls of the tank. And of course, blind thermocouples are not measuring true temperatures. So the Cyclops is used to make a measurement during the reversal cycle at a precise point when the flames are out for a given length of time. Now, what you can imagine is that making a temperature measurement with a Cyclops takes time. The optical profile, as we've discussed in the previous slide, is monitored by taking several point measurements along the walls of the tank to look at the shape of the optical profile. Now, to take an optical profile using a Cyclops unit can take several hours. However, what you can see here is we have the NIRB glass true thermal imager for monitoring temperatures within the glass tank. So this is using a thermal imaging device which looks along a lens system here, such that the actual thermometer, the detector, the important part, can be stabilized outside the glass tank to give accurate and stable measurements continuously inside the glass tank. And as you can see here, you can actually measure at any location continuously, either along the walls or anywhere on the refractory. And this allows you to capture very precisely the temperature in the tank at a given time during the flame out, between the reversal when the flame is not present. Now, we still use the trusted Cyclops as a cross-check, and we still use the Cyclops as a cross-check because the operators looking inside the glass tank and making these measurements, looking inside the tank is a very important part of the general process, just to monitor the condition of the glass tank. So what we're doing is we're complementing the use of the Cyclops with these new devices, these continuous temperature monitoring devices, which actually give us 324,000 pixels. So each of those measurement points is replicating what you see with the Cyclops portable. And the important thing to recognize here is the reason the Cyclops works so well is that the filters in the Cyclops filter what is the combustion gas out of the measurement. There is no effect from the combustion gas on your measurement. It also measures from a very, very small area. The Land thermal camera measures at the same wavelength precisely using the same filters as the Cyclops. So everything you're measuring with the Cyclops is directly transferable and relates to the thermal camera data. So that's very important because we all have in the industry many years of operating glass tanks and many years of data. So that historical data allows you to continue managing and developing your process. What I'm showing here is also the industry standard for gas measurement. Now the Landcom Portable is a 9-gas analyzer and it has a very stable long-term reading for NOx. So this is a 0.5% accuracy analyzer with a battery life of up to 8 hours, and when it's reading, it will read throughout that time accurate NOx measurements. You may know that a lot of the systems that are on the market, the portable analyzers, when they get to half battery life, they will stop measuring NOx. So NOx being the important gas we're trying to monitor, this analyzer allows us to take measurements in what's called the port necks. So we can use a portable device with an extended ceramic tube to make spot checks of the various gas compositions in each of these locations from the back of the regenerators. So if we look at this as a tool, let's look at this new technology that's coming to the market. We've been making these infrared cameras now for maybe 5-6 years. There's about 50 to 60 installed continuously monitoring inside glass tanks. And what we can see here is the power of online temperature monitoring. You are seeing what is a recording. So this is an actual recording taken inside the furnace with the NIRB camera. And it's showing you continuously the optical profile. And within that profile, it's displaying the maximum temperature that we see along the line, the minimum temperature along the line, and also the point at which the cursor here is located. And the cursor is displayed by a little red cross on the display. So it's showing you exactly where the highest temperature along that line is being monitored. Now, that's quite important because it not only gives you the hotspot, but it also shows you the shape, the energy distribution within the glass tank. So this allows you to do a great deal of work in terms of optimizing the fuel that's going into the tank. Now, because you're measuring the whole area, you can also look within the tank if there's any areas that are getting too hot, and particularly if there's any areas that are getting cold with air ingress, which wastes energy, totally waste of energy if you have an air leak into the furnace. And if you have an air leak into the furnace, you get condensates, and the condensates will destroy the refractory. So asset protection using this device is a very important part of what we're giving as part of the solution. So you can see by monitoring the area for high temperatures, you will protect damage occurring to the refractory within the tank. So bear in mind that what we have here is molten glass. So in the bottom of this tank here, we're looking at something which is in the region of maybe 1600 degrees C. The wall temperatures and the crown are heated to maybe 1560, 1600. But the maximum temperature before you cause damage is somewhere around 1620 to 1650 degrees, depending on the type of refractory that's used. So now consider these flames. The flame temperature here is around 1800 degrees C, and the oxy-fueled flames are somewhere around 2700 to 800 degrees C. So if you have any impact from the flame, if the flame is touching the furnace walls, there is a huge potential for damage. Moving on to a different representation of the data. So the previous slide showed you what was the traditional heat profile, where the heat intensity within the furnace is being represented by colours. What we've done on this particular slide is reverse. So we've now got a monochrome image in negative form. And we do this because it allows us to see very clearly areas where there is air leakage, where there's low temperatures. You can see the low temperatures occurring here. You can see the issues along the melt line here. So this particular image gives us a lot more clarity. It allows the eye to see things within the picture that perhaps it wouldn't otherwise have seen. And this also, within this image, is showing you a very simple way of monitoring the batch as it comes into the furnace. Now, this particular example shows what is a very poor distribution of batch, and what we're forming here is something called a pipe or a snake, which is very bad. But what we're looking at here is an alarming system that tells us when the batch is moving forward within the furnace. So as the batch moves forward, if it crosses this line, this critical line, then we can create an alarm within the software very simply. So there's a number of different features, different factors that this software can be used for. Within all this, one of the key elements is preventative and predictive maintenance. So what we're showing here is the ability to select a different or part of an area within the thermal image and to use the zoom facility to make closer examination of the part to decide how critical it is and whether or not that furnace needs repair. And repairs are very expensive. So being able to monitor, prevent, and when you find a repair, quantify is obviously very important. The screen that we're showing here is a screen which shows what are called isotherms. And this particular screen is one which creates an impression of visualization of the data, showing very quickly the temperature distribution within the furnace itself. So you can see here the red isotherm is showing the higher temperature distribution across the crown. So you can see here how there is a skew on the temperature here. So this will have occurred because of the firing cycle. So you would expect this to reverse when the furnace is being fired from the other side. But what you can see here is the cold areas within the furnace. So in this particular furnace here, we have one side of the furnace which is much colder than the other side. So that could be an area of concern. And finally, within this image, we've got something showing what is the basic flame shape. So we can see how the energy is being formed, where the energy is being formed, and how that is being impacted, how it affects the overall furnaces. And then finally, what I want to look at here is the flame shape, because what we can do with the camera is we can look at using an integrator, and the integrator comes on. We see then very clearly where the highest temperatures within the flame are being formed. This allows us to use the thermal camera for evaluating the flames that are likely to be causing the most NOx within a furnace. And this is a huge step forward. This is the data, this is the work, this is the research that we're presenting currently at Glass Problems and various conferences around the world, because this really is groundbreaking technology that the glass industry can use to be able to optimize the process. And as a result, AMETEK Land were the winners of what was the Glass Focus Award in 2017 for an innovative solution where we've applied this technology in collaboration with Simpson Combustion and NSERC. Many of you will know the NSERC company has some of the largest container producing plants in the world. So it was a real challenge to optimize the furnace, and we do have case studies giving some details of that process that was undertaken at NSERC, and you're welcome to download those from our website. So in summary, if we look at the applications in the glass tank, what we have the Cyclops for measuring the crown temperatures, or the port arch temperature as it's called, or indeed the regenerator temperature. Now these are all single point measurements. So this is a spot measurement. The operator goes out, takes a measurement, and retires back to the control room. The NIRB, the camera, however, gives us exactly the same data, 300,000 measurement points. It's very similar to the Cyclops, in fact directly comparable with the Cyclops, continuously. And not only continuously, but recorded for comparison as the recipes change, looking from melt to melt. Now there are also the use of fixed thermometers. We use single point thermometers for measuring inside the regenerator, and also fixed thermometers for measuring up onto the crown. So Land has a comprehensive solution for monitoring what is the glass melt tank from the infrared perspective. We then complement that with an accurate gas analyzer, and also what is the flue gas analysis, the chimney analysis, the stack analysis, which is the continuous cross-stack opacity meter. And this cross-stack opacity meter meets all the US legislation. So it's designed to be something which is highly accurate, highly stable, and gives a good feedback for what is the maintaining legislative control of emissions from the stack. So, coming back to our old friend Maxwell Planck and looking at the Planck law and the curves that I've shown you, just one thing that I'd like to sort of show you about the glass industry particularly is that we do have some specific challenges. And I guess the main challenge is shown here, and that is that when you look at soda lime glass, depending on the wavelength of operation, so it depends on which particular thermometer you choose, you will see different amounts into the glass surface. So just remember, the reason that we use glass in the first place, in most cases, is because we can see through it. So if our eyes operating between 0.6 and 0.7 microns can see through the glass, our infrared thermometer working at 1 micron will see through the surface. Now, what we say on molten glass is that we can see, on clear glass, we see, I think, up to about 100 millimeters into the surface of the glass. Now, the energy is collected within that glass. It's a little bit like looking into the mist or into the fog. Your eyes can only see a short way and can only define something within the mist over a short distance. But actually, you can see further and further, but your eyes lose clarity. And it's the same with the infrared thermometer. Most of the energy is coming from just below the surface and into the surface, but it will see through something that is maybe only 40 millimeters thick. So that becomes quite important on some of the applications, and so you'll see why, as we go through the presentation and we look at different ways of measuring glass itself, why this is important. If you look at the range of temperature thermometer devices that AMETEK Land produce, then what we can see here is that this set of curves gives us a good understanding of why we make thermometers that work at 1 micrometer, 1.6, 2.4, and this critical 5 micron, and the longer temperature, longer wavelength, 8 to 14. And the reason for this is that if you look at the transmission of the glass, what we find is that the glass will transmit energy down to a point where it becomes opaque at the 5 micron region. So what we tend to do is, if we're looking for molten glass measurement, where we have a reasonable bulk of glass, we will always use a 1 micron thermometer. So the Cyclops is 1 micron, the model FG, which is an industry standard, a legend product, is working at 1 micron, and the NIR boroscope is also working at 1 micron. So this is our critical measurement here, which is used for molten glass measurements. So we get a good reading for what is process control. Now, in some applications where you might have, for example, in the fiberglass industry, you have a small, narrow stream of glass that's being formed. And in those cases, we sometimes use slightly shorter wavelengths so that we don't quite see through the glass to give us an accurate reading. But where we progress is that after the melting process, when the process is forming, for example, flat glass, when we're making glass in windows, what we're looking for there is something which doesn't see through the surface. And that's where the 5 micron thermometer becomes the industry standard, because we see only the surface of the glass. Just to recap slightly, one of the things that we need to take into consideration is the emissivity factor. Now, many of you will have understood, maybe know a little bit about emissivity. We've explained how that correction factor is applied, but what you might not realise, it is a surface effect. So if you take a stainless steel kettle in this case, and you simply paint the surface, you'll get very different levels of radiation emitted from the black circle compared to the shiny stainless steel circle. And we see this all the time in industry. And this is a comparison between what is the glass mould, which is very shiny, highly reflective, and our eyes can see that, compared to perhaps what is raw batch, which is very matte finish, very broken. And what the eye tells us in this situation is that this is a very high emitter, a diffused emitter. In this case, it's a specular low emissivity emitter. So what we have to think about is these different values that we might need for emissivity. We've already said that to determine emissivity, what you need to do is look at the manuals. There are a lot of reference manuals which will give you different emissivities for different materials. But what's important to recognise is that the surface condition, if the surface deteriorates, if the wavelength that you are measuring at changes, very critical. Remember, the Cyclops and the NIRB and the FG all measuring at precisely the same wavelength, so the same emissivity applies. Viewing angle has an effect. Now this is more on the shiny glass mould, for example, where you've got a specular reflector. If you look at a normal, for instance, the painted walls of your office, they are a diffused reflector. So the angle effect becomes less significant when you're looking at something that's a diffused reflector. Temperature can also have an effect. So when we're looking at emissivity, one of the critical things, and one of the things that I often say in my presentations, is please set the emissivity and then do not adjust it. Because if you set the emissivity for your process and you do not adjust it, the data, the historical data, all becomes valid. So providing you're having the thermometer calibrated at a regular interval, maybe every 12 months, then you will have good quality, traceable, reliable data that you can use not just within the plant historically, but from one plant to another around the world. So if you're a company, if you're looking at companies that have got many plants in not just different locations, but different countries, you want traceable, accurate, reliable, and stable temperature measurement that's traceable. Now, if we look for a minute at the thermometer optical system, what we're looking at here is the area term that I referred to earlier. And that is that if we look here, this thermometer has a field of view focused down to measure within this area. And it's important that when you're taking a temperature measurement, you completely fill the field of view. Maybe obvious if you think about it, and that is that if you don't fill the field of view, you don't get all the energy. So if you look at a small target, you will only receive from that target a limited amount of energy. You will not get an accurate reading. So what we would look at doing is making sure that the object we are measuring completely fills the area. A small target in that area will not be measured. Now, some of you will know about two-coloured thermometers or ratio thermometers, and I give a riveting lecture on the use of these thermometers. But it's suffice to say that in 90% of applications, certainly within the glass industry, the standard single wavelength thermometer is by far the best choice. Now, looking again at the reasons we all use the Cyclops has a very accurate focusing down to a specific point here. So if you think of the measurement that we've just talked about, focusing becomes very important with an infrared thermometer, because if you focus, say you're trying to measure something here and you're focused at this point here thinking that you've got the right diameter, then this field of view has opened up past the focus point. So many thermometers that are out there in the real world don't measure from the location that they say they're measuring from. The Cyclops is precise, and that's the reason we use it. You can measure through a peephole onto the far side of the furnace with accuracy and repeatability. When we start looking at glass gob measurement, and this is a thermal image taken of a glass gob using a 1 micron thermal camera. So what we can see here is we're looking through the surface. You can see certain effects, certain non-uniformity of the glass as we're looking through that surface. But the reason for putting this particular slide up is to show that with a large gob of this size, we would get good, reliable, repeatable measurements looking perpendicular onto the actual gob itself. But when we're measuring smaller gobs, and certainly when we're measuring below the forehearth, it's always recommended that you would measure up, looking into the neck of the forehearth. This increases the path that the Cyclops is looking at within that glass gob, and particularly if you've got very small gobs, we would look up into the mouth of the actual forehearth itself to give us a good, reliable reading. Now, what you can see here is this: the Cyclops has been replaced by what are fixed thermometers, and this is a thermometer here with the optic head in a cooled and purged housing to keep the lens clean, and it has a fibre optic cable. This is a fibre optic cable that runs back to the amplifiers. So the actual amplifiers of the system are outside the hostile area, and that's where you get the stability. So there is always a solution where we can migrate from having the portable onto a fixed system, which gives us then more reliability of the reading, because you take away from the reading the variations you get from operator to operator. And we have a number of successful installations around the world which are continuously monitoring and tracking gob temperature. Moving swiftly on to what is the float production process, because now we've looked at what is the molten glass applications, and what I want to look at here is the tin bath application and the layer. Now, there are some great books written about the glass production process, but what I'll do is keep it simple. We melt the glass in this region, we refine it here, and then the glass is pulled onto what is called the tin bath. So this is the tin bath area, and as its name suggests, the glass itself floats on top of liquid tin. Now, at this point, it's very important that you don't measure through the glass, you only measure glass surface, otherwise you would measure the temperature of the tin. Fairly obvious, really. So at this point here, what we need to be doing is looking at our 5 micrometer thermometer. So we only measure glass surface, and Land Instruments, AMETEK Land, have a range of thermometers here for this application to give accurate, reliable readings. And when we come out of the tin bath, we then go into the annealing layer here. As the glass flows down this annealing layer, the stages of cooling are absolutely critical, where we would look at going from what is a single point device, looking at perhaps just the center line, or even multiple measurements onto the scanning devices. Now, the beauty and the reliability of the scanner comes from the fact that we have a single detector here, so a single stabilized detector and a rotating mirror. So the same detector is measuring here as is measuring here and measuring here. So the relative temperature measurement is of very high repeatability and stability. Now, within the scanner, we actually measure 1,000 measurement points over an 80-degree scan. So we build up what is a very comprehensive thermal map of the actual process. Land has a full glass layer solution. So we have put together our knowledge over the years to produce a rugged housing that's suitable for mounting on top of the glass layer with a sighting cone. The sighting cone here has to seal the gases, and that gives us access to measuring across the full width of the glass. And from that, we use the software to produce what are these thermal maps and temperature profiles, a temperature profile across the glass. So these are critical measurements, critical parameters for any manufacturer of float glass. If we look at the production of windows, float glass, in the modern architectural theme, we are looking at many buildings being made which are then covered with glass. Now, the standard glass, as it comes from the float line, has not been tempered, it's not been stress relieved. And if you remember the old vehicles, the old cars, we used to have windscreens which shattered into shards and were very dangerous. The modern windscreens are all tempered, they break into small fine particles. But one of the main reasons for tempering is, as you can see here very clearly on this image, is the reflection. Our eyes are very sensitive to what is the reflected energy coming from the building. And if you see something that looks all misaligned, then that glass has not been tempered. Even if you see one pane among the whole facade of a building, your eye will be drawn to that pane. What we're looking for is nice flat surfaces so that we get this lovely beautiful reflection of our skyline, and that's using what is the glass tempering process. And the way that the tempering process works is that sheets or lights of glass are put through a heating furnace where they're heated to a precise temperature and then cooled in a controlled way. And only by performing this market process do we get the quality of glass that we're looking for in our buildings. Now, some of you will have heard of low emissivity glass or low E glass or low energy glass. Now, this is glass which is coated or covered so that some of the energy is retained and sunlight is reflected. So it's low energy glass. And in this application, what we find is that the emissivity of the glass surface has dropped down to values as low as 0.3 or even 0.1. So we have to add artificially a huge amount of signal to give us an accurate temperature reading. And furthermore, this emissivity value here can vary from batch to batch as it is passed through the furnace with different processes. So what AMETEK Land have is a solution where we automatically compensate for what is the emissivity changes. We use single point thermometers to measure the underside of the glass, and we correct the emissivity on the fly in the scanner that's measuring the top surface, giving us an accurate and reliable repeatable temperature reading. Now what you can see here is there's a very small gap normally between what is the tempering furnace here and the air quench here. And because it's a small gap, again, you need a thermometer solution with precision optics. And it's the precision optics that gives the Land its class-leading performance. It's the stability of the electronics and amplifiers that allow us to have the gain and stability to compensate for these low emissivity, low E glasses in this application. And again, we present the data to an operator in a way that is giving the operator a very visualization of quite a complex thermal map. And you can see here very quickly, everything that's green is within tolerance. The red areas are over temperature and the blue are under temperature. So an operator gets immediate feedback and can take action. And finally, when we get to the low temperature applications, we must move, and we're forced to move, to what is the 8 to 14 micron region. These are general purpose measurements. these are the devices that we all have, the small handhelds that are low cost and low accuracy. What we can do is, again, by stabilizing the detector, by stabilizing the electronics, we can get accurate readings. So for the glass industry, what we can see here is the exit of the annealing layer on a container plant, where we can look for the temperature distribution across the layer using what is a thermal camera designed for the lower temperature range of measurements. And indeed, on this side here, you can see there's mold temperature measurements, and these mold measurements again are used to look for the cooling and the effect of cooling on the mold. So normally for development purposes rather than online continuous measurement. But I wanted to stress the point that Land as a company has solutions which run all the way from the start of the process right through to the very end. So this is the industrial arc camera. This camera, as you can see, fits in the rugged housing to protect it. So it will work in these hostile environments. And it's protecting cameras, putting them in an environment where the detector can has the stability to be able to give you online, continuous, reliable measurements and performance.
Okay, Mark, thanks so much for that great presentation. Okay, Mark, here's your first question. How is the technology applied to measurements in the forehearth, and does color affect the measurement?
That's a very good question. Indeed, AMETEK Land offers the Model FG, the forehearth glass thermometer, which is a bulk glass measurement, a 1 micron measurement, which is specifically designed for use in the forehearth and the distributors and feeders. Infrared thermometers are used in this application simply because there's no disturbance, there's no contact in the glass, so there's no possibility of disrupting the flow along the forehearth. They give very, very quick response to the changes in process conditions for control purposes, and no drift, unlike thermocouples, which of course will drift with time. Fairly slow responding thermocouples, and one of the limitations of thermocouples is that as the glass depth changes in the forehearth, it does affect the reading of the thermocouple. The FG thermometer is quite remarkable, really. It's a thermometer that was designed in 1984, so it's been on sale now for more than 30 years. It's a legend. It really is a legend product. Many of you will remember the product as being the FiberTemp or FiberTemp 2 before it became the Model FG, and it's used extensively simply because of its reliability. A key factor of this measurement is the interchangeability, the ability to swap one thermometer to another and have an accurate, reliable, repeatable reading within 2C. Now, what we find on glass plants, and particularly plants right across the world, is the ambient temperatures where the electronics sit will vary quite considerably, and not too many companies take care of this. The Land FG will operate over a very wide range with stable conditions. Now, to achieve the interchangeability, to achieve that stability, requires precise calibration. Every FG is set up in our factory against a reference standard, so every FG in the world is traced back to our own internal standards. And it's important to recognise this because as we use the instrument on different plants, all of the data is then transferable. If we look at the effect of colour, particularly on the reading, what we have to appreciate is the forehearth, of course, is quite dynamic. It's looking to cool the glass from the outlet of the tank down to a very precise gob temperature and to maintain that gob temperature. Now, what will happen as a result of colour change is that if you consider clear soda lime glass, we probably have, as we've said, a penetration depth of up to 100 millimeters. Most of the energy coming from 20 to 40 millimeters below the surface. If you change to a different colour, depending on the colour, will change the depth of penetration, even to as much as probably an order of magnitude on the figures I've just given. So you're actually measuring closer to the surface of the glass. Again, the depth of penetration, the level of glass will not affect this. It will always be a constant reading. So recipes, an understanding of the consistency of glass will remain the same. But the temperature profile, and there will always be a temperature profile across the glass in the full hearth. Of course, the change in actual depth that you're measuring will affect that reading. Just the same as with a thermocouple, changes in level will affect that reading. So, hope that answers the question. Anything further, please drop me an email.
Okay, thanks, Mark, for answering that question. Now, we're just about out of time, so let's take one more question before we wrap up this webinar. How often should infrared devices be calibrated?
The question of calibration and maintenance is a question that I'm often answered, and it's something that I answer with a question, which is how important is the process? Typically, an actual genuine traceable calibration is normally required as part of the audit, part of this ISO standards, every 12 months. Now, if you're calibrating the instrument every 12 months, that's the electrical calibration. You also need to recognize that this is an optical device, and therefore the services provided to the instrument, the airflows for the purge of the lens, the filters need to be checked and cleaned on perhaps a monthly cycle, depending on the contamination within the plant. But that said, there are some applications, and I know that from personal experience where I've been involved with a major engine provider in the aerospace industry, their thermometers were checked on a weekly basis. So again, it's a question of the process as how often to be calibrated. In most cases, every 12 months is adequate. AMETEK Land do provide a full service and support package. We can offer maintenance contracts for our customers around the world, and they're based on your specific requirements. So they are flexible and tailored to your needs. Again, any questions or further information required, please don't hesitate to drop me an email.
All right, Mark, we're going to have to wrap things up right there. Mark Bennett, thanks so much for taking the time to be here with all of us today. And a special thanks to all of our audience members for being part of this webinar event. Take care and have yourselves a great day.